So far, when we've been graphing, we've looked at linear functions, quadratic functions. We did a little bit on circles, and then polynomials. So linear functions, quadratic functions, they are polynomials. And then we sketched graphs of polynomials. In chapter 5, we're going to be graphing other functions. We're going to start off in 5.1 with probably the most complicated function to graph, which would be the rational functions. And the reason why the rational functions are so complicated is because they are rational, so fractions, where the numerator and the denominator are polynomials. So we've seen how large polynomials can get. Though oftentimes these rational functions can get very tedious and complicated to graph. So what I highly recommend as you're going through graphing rational functions is to double check with a graphing calculator or a graphing utility such as Desmos. In this section, we're just going to focus on two basic functions. The first one that we're going to look at would be this reciprocal function, which is 1 over x. Something to notice is that because x is in the denominator, that means that my x value cannot be equal to 0. That means that the domain is going to contain everything except 0. So the domain is going to go from negative infinity to 0, union 0 to positive infinity. Since it can never be equal to 0, and my domain has now been split up into two intervals, if you look at the graph of 1 over x, you see that it has two pieces. And where it splits off is at the y-axis. So think about what that is. The y-axis is where our x values are 0. And in fact, the y-axis is the vertical line x is equal to 0. Imagine taking any point on this y-axis, and you'll see that the x value is always 0, which is why my graph will never touch or never cross the vertical line x is equal to 0. So we call this vertical line that the graph will never touch or cross, we call it a vertical asymptote. And then I don't want to keep writing vertical asymptote over and over and over again. So I will often abbreviate this as just VA for vertical asymptote. So an asymptote is simply a line, or it could be a curve, but in this case it's a line that your graph will follow. Notice as our graph gets closer and closer and closer and closer to our vertical asymptote, the graph just follows it. With a vertical asymptote, your graph will never cross or touch, because think about that. That's when your x value is 0, and in the case of this function, that would mean the function is undefined. So since 0 makes our function undefined, the graph will never touch or cross this vertical asymptote. It'll just follow. Now look at what happens as we come in from the left-hand side and we approach the line x equal to 0, or the y-axis. Notice that the graph will go down towards negative infinity, but it follows your vertical asymptote. With this particular graph, also notice that as x's get large, going to positive infinity, this particular graph approaches the x-axis. It's not touching or crossing it in this case. So since it's approaching the x-axis is also an asymptote, but since the x-axis is a horizontal line, we use the language horizontal asymptote, which I will abbreviate as HA. Our reciprocal function 1 over x has a vertical asymptote, which is the y-axis. The equation of that vertical asymptote is x is equal to 0. It has a horizontal asymptote, which would be the x-axis. The equation for that horizontal asymptote would be the horizontal line y is equal to 0. So again, if you look at the graph and you look at what happens when the x values goes towards negative infinity, so getting smaller and smaller and smaller and smaller, our graph is approaching that horizontal asymptote, which is our x-axis. So again, asymptotes, your graph will approach and follow. In the case of a vertical asymptote, never going to touch or cross because that's where your function will be undefined. However, in the case of a horizontal asymptote, it is possible for a graph to touch or cross it. Because what the horizontal asymptote is giving us is end behavior. Think back to the polynomials and we're looking at the ends of the graph. In the middle, it did all sorts of funny stuff, but the ends went somewhere. In this case, the ends are following the horizontal asymptote, but in the middle, it is possible to touch or cross. This particular rational function does not touch or cross its horizontal asymptote, but some might. Looking at the range for this particular function is going to be negative infinity to 0, union 0 to positive infinity. So going back to the graph, you can see that you get all the y values except for 0. And then these bullets have some little fun facts about these graphs. Notice that our function is a decreasing function. As the x values go from left to right, the function is always falling or going down. Starts high, goes low. It's also discontinuous when x is equal to 0. There's a break in our graph and it breaks into two pieces, which makes sense because we have two pieces to our domain. And then it describes the y-axis as a vertical asymptote, x-axis is a horizontal asymptote. And we'll go into more about the way you define the horizontal and vertical asymptotes in the next section. But also, this function 1 over x is an odd function, so its graph is going to be symmetric with respect to the origin. Imagine taking this graph and rotating it 180 degrees. The graph will stay the same. It will have the same shape. The other basic graph we're going to look at is what we call the reciprocal of the squared function. So that's going to be similar to 1 over x, but instead in the denominator we're doing x squared. So because it's x squared in the denominator, that denominator will never be negative. It'll always be positive, or it'll be 0, which it cannot be because then we'll get 1 over 0, which is undefined. So we can't have an x value of 0. That leads to a domain that is broken up from negative infinity to 0, union 0 to positive infinity, similar as with the reciprocal function. But because the denominator is never negative, that's going to change our y values. That's going to change our range. Notice that the graph is always above the x-axis, which means our y values are always positive, so the range is just 0 to positive infinity. However, with this reciprocal of the squared function, 1 over x squared, we still have the same horizontal and vertical asymptotes. Notice that the graph, if we're going to approach 0, which would be the y-axis, and again, that y-axis is the equation x equal to 0. The x-axis is the equation y equal to 0. So if we were to approach x equal to 0, that line, and we're coming in from the left, from the negative side, we're going to go up and follow our asymptote. If we're coming in from the right-hand side, we're going to go up and follow our asymptote. If we are coming in and looking at x values that are getting larger and larger and larger and going towards positive infinity, the graph approaches the x-axis, which is y equals to 0, which would be our horizontal asymptote. And as x goes towards negative infinity, the graph approaches the horizontal asymptote y equal to 0. So same asymptote, it's just that there's no negative y values. So here, this is an interesting fact that 1 over x squared, that's actually increasing from negative infinity to 0, decreasing from 0 to positive infinity. So let's look back. Yes, notice that as I go from left to right, the graph rises on the interval from negative infinity to 0. But after 0, the graph falls as the x values get larger and larger and larger. So it's decreasing. At x is equal to 0, it's discontinuous. And again, y-axis is the vertical asymptote, x-axis is the horizontal asymptote. This is an even function, and that just means that you see a reflection. If you were to reflect about the y-axis, you would get the same graph, or imagine folding along the y-axis, the two halves would match up. We're going to use these two basic functions and use our prior discussion of transformations to graph 3 different examples. In example 1, we want to use transformations to graph this function, and then we're going to give the domain and the range. First of all, I'm going to rewrite this. This is actually equal to, if I were to factor out the negative and put the 1 over x in parentheses, and then have the plus 2 on the outside. And also remember, you can always replace the f of x with y, if that's more comfortable for you. So what that tells me is that the 1 over x, that's going to be my basic function. So I know the shape of that graph. The negative on the outside is going to be a reflection, but the 1 over x, that function's already done its job. So the negative on the outside is going to affect the y values. Negative y values will flip up to positive, positive will go down to negative. And then that plus 2 is also on the outside of the function, so that's going to be changing the y values, and it's going to be a shift up by 2. So again, use Desmos to double check, because these can get very complicated. And I'm going to use some really light colors to graph 1 over x first, and then I'm going to transform it by doing the reflection, that negative, and then I'm going to shift it up 2. So our initial 1 over x, it's going to pass through the key point 1, 1, and then follow the asymptotes, and then negative 1, 1, follow the asymptotes. So going back to that negative on the outside, that's going to reflect the graph. So everything above is going to flip down to below the x-axis. Everything below the x-axis, it's going to flip above. So I'm going to use a different color here. The point 1, 1 is going to be 1, negative 1. And it's going to follow the asymptotes. The point negative 1, negative 1 is going to be negative 1, 1. So that's going to flip up, but still going to follow those asymptotes. So my asymptotes have not changed, which means my domain and my range did not change. But now I have the plus 2. So the plus 2 means I'm going to shift all of this up. So let me just for a second remind you that we had a y equal to 0 horizontal asymptote. When you shift up or down, remember you're shifting your y values up and down. So that means you're also going to be shifting your horizontal asymptote up and down. So the plus 2 shift, what that's going to do is it's going to take my points, which here would be the point negative 1, positive 1, and it's going to shift that up 2. It's going to take the point 1, negative 1, and shift that up 2. But it's also going to take my horizontal asymptote and shift that up 2 as well. And I'm going to use a dotted line for my, or dashed, to show where my new asymptote is. So now my graph is going to follow. That vertical asymptote did not change, just the horizontal. And follow. Okay, so sometimes it's helpful to label a few points. Maybe I'll do that in red. I have the point 1, 1. And then I have the point negative 1, 3. Right, so these are my 2 points. These can get very messy. Again, I'm going to keep saying this. Use a graphing calculator. Use Desmos. But here we're using transformations. Now later on, I'm going to kind of go away from the transformation because you can imagine these are just very basic rational functions. Notice that there was a 1 in the numerator and just an x or an x squared in the denominator. So transforming these, not so bad. But remember, it's a polynomial over a polynomial, and those polynomials can get pretty long. Imagine having a 4th degree polynomial over a 5th degree polynomial. That's crazy. So for now, we're using transformation, but we're probably going to move away from that when we get into our later section. Forgot. I have to talk about domain and range. Got all involved with our function. So our domain did not change. Remember that those are the x values. And when you think about our vertical asymptote, which is x values, x equal to 0, that didn't change. We still have the same vertical asymptote. Maybe I'll just go ahead and highlight that in blue as well. So it's still the same. Domain's going to be negative infinity to 0. And then union 0 to positive infinity. What we did change was we changed our range. We shifted that horizontal asymptote up 2, which means my y values are going to go from negative infinity to positive 2. Oh, look, I put y is equal to 0. Why did I do that? Because it's me. So it's going to shift our y values as well in our range from negative infinity to 2 and then 2 to positive infinity. I have this thing where when I'm talking and I'm writing, I'll write down something completely different. So negative infinity to union to positive infinity. Let me double check everything. Yes, that looks good. In example 2, we're going to do the same thing we did for example 1. We're going to identify our basic or parent function and then graph our transformation. I notice that I have x minus 2 squared in the denominator, so that tells me that my parent function is 1 over x squared. I'm going to go ahead and graph that. Key points would be 1, 1. So it's always nice to have your key points, easier to move those around for your transformation, and negative 1, 1. So remember that reciprocal of the squared function means that the graph is above the x-axis. The minus 2 in the denominator, and that's x minus 2, says I'm changing my x value. So remember, we do opposite. Instead of taking away and moving to the left 2, we're going to actually add and move to the right 2. My next transformation would be to move to the right 2 units. I'm going to take this key point 1, 1, move it 2 to the right. So now it's at 3, 1. Negative 1, 1 moves to the right. It's now at 1, 1. But remember, we're also moving our asymptote, our vertical asymptote, that's x values. And we are transforming x values. So we're now at a vertical asymptote at x equal to 2. And our graph is going to follow the vertical asymptote. Horizontal asymptote did not change. So we're going to follow that as well. Our last transformation is a minus 3. That would be a shift down 3 units. So if I take these points, 3, 1, and I shift 3, 1 down, 1, 2, 3. I take the point 1, 1, shift it down 1, 2, 3. But don't forget, I'm also shifting my horizontal asymptote as well. That is going to shift down 3 so that the horizontal asymptote is now y equal to negative 3. My graph has to follow the vertical asymptote. This did not change. I'll go ahead and redo this in blue. So that didn't change. So we follow vertical, follow horizontal, follow vertical, follow horizontal, and the blue graph would be my final graph. So when we talk about the domain and the range, in this case we change them both. I shifted my vertical asymptote from x is equal to 0 to x is equal to 2. So now if I put 2 into my function, the function's undefined. So I have to take 2 away from my denominator, or my domain. So now it's going to be negative infinity to positive 2, and then 2 to positive infinity. So again, we shifted vertical asymptote, domain changed. But we also shifted our horizontal asymptote down to y equal to negative 3. So now if you look at the graph, all the y values are greater than negative 3. That changed our range to negative 3 to positive infinity. Last one, little strange. It's not quite a 1 over x. In this particular case, we need to write it so that we can clearly see the transformations. I don't see the transformations when it's written as x plus 1 over x minus 2, which means I'm going to use long division to rewrite this function. Recall that long division of polynomials says you take the top, which is x plus 1, and you divide it by the bottom, which is x minus 2. So again, we have to ask ourselves, what do I need to multiply this x on the outside by so I get the x underneath the division bar? So I'd have to multiply that by a 1, so that's our quotient. 1 times x minus 2 is x minus 2, and then we subtract down. So x minus x is 0. 1 minus a negative 2 would be a positive 3. And we write it as 1 plus the remainder of 3 over the divisor of x minus 2. So I can rewrite this function, and I'm just going to use y, as y equal to 1 plus 3 over x minus 2. I'm going to rearrange this so that I can clearly see what my transformations are. So I'm going to switch the 1 with the 3 over x minus 2. But I'm also going to factor out the 3 from the numerator, and in parentheses write 1 over x minus 2. And you don't have to do this. But now how it's written, it's easier for me to see all my transformations. I actually have 3 transformations. Inside the parentheses, that x minus 2 tells me I'm going to shift 1 over x, which is my basic or parent function. I'm going to shift 1 over x 2 units to the right. And then the 3 on the outside of the function says I'm going to multiply my y values by 3, which would be a vertical stretch by 3. The plus 1 says I'm going to shift my y values up 1, so a shift up 1. Let's go ahead, and this is going to get messy. Let's go ahead and graph our basic or parent function. Passes through 1, 1, and negative 1, negative 1. So it's the reciprocal function 1 over x. And then I have that x minus 2. I'm going to shift the 1, 1 over 2, so it's at 3, 1. I'm going to shift negative 1 over 1, 2, so it's at 1, negative 1. However, remember, we're also shifting our asymptote as well. So it's not x is equal to 0 anymore, it's x equal to 2. I'm going to sketch that in. And then we follow the vertical asymptote. Horizontal asymptote did not change, so I'm following that as well. And we have our first transformation. Okay, let's look at the next transformation. That was a 3 on the outside. So a function already did its job. The 3 on the outside is changing the y values. We're going to multiply the y values by 3. At the point 3, 1, the y value of 1, if we multiply that by 3, 1 times 3 is 3. And then at the point 1, -1, if we multiply -1 by 3, we get -3. When we do the vertical stretch or shrink, we're not changing our asymptotes. We're just stretching out our function. So it's still going to follow the same asymptote of x is equal to 2 and y is equal to 0. So you see how it's stretched out? X is equal to 2, y is equal to 0. Now I'm going to take that graph and plus 1. So I'll use black for this. I'm going to take the point 3, 3, and I'm going to shift that up 1. But also remember that what I've done is I've shifted my horizontal asymptote up 1 as well. That would now be y equal to 1. And then at this point, 1, -3, that's shifted up 1. Then I follow my asymptotes. I'm going to put the x equal to 2, that vertical asymptote, in black as well to remind myself these are my final asymptotes that I need to follow. All right, that is the transformation, and you can see how complicated it gets when you have more than 1 to even 3 transformations with these rational functions. So in the later sections, we'll look at other ways that we can graph, but that's it for this one. Notice that this question did not say to find the domain and range, but let's do that anyway, because we've changed them both. Our domain has now changed because we switched our vertical asymptote. So now that the vertical asymptote is x is equal to 2, we're going to go -infinity to 2, union 2 to positive infinity. And our range also changed. We're going to go -infinity to a +1, and then 1 to positive infinity. Okay, so that's it.